Hi everyone, I'm Nora and I was supposed to talk about mixed quantum classical methods for molecules in cavities, and I will today do that virtually. So, our main motivation of doing what we are doing is to start to develop ab initio methods for a full electron-photon nuclei correlated system. And in our case, we started to develop the so-called MTE approach for photons. So it's a multi-trajectory Ehrenfest approach for photons, where you simply, to the already very well-known mixed quantum classical setup for electron-nuclei interaction, add a sampling for the photons to introduce quantized light fields. And if we want to do so, we have to answer the first question: how do we sample those photons? And the answer to this is quite simple. Because we have at time zero only a vacuum fluctuation of our cavity, all our photon modes are in their vacuum state, and if you Wigner transform those vacuum states, you simply end up with Gaussians. So what we're going to do is randomly sample out of those Gaussian distributions, and with this set up our initial state, and then we're going to propagate this initial state via, in our case, mean field Ehrenfest, and do this a couple of times, sum over all those trajectories, and then get our observable of interest. And we started to benchmark this idea now with two different setups. The first one was a pure electron-photon correlated system, where we wanted to check if our method is capable of describing one or two photon spontaneous emission. And then, because we want to make our way to realistic systems, also for sure needed to include the nuclei degrees of freedom. So you can simply also add a sampling for the nuclei degrees of freedom. And I will discuss how this method can, on the one hand side, how it can describe suppression of proton-coupled electron transfer, and mainly will in this talk focus on how many photon modes will influence this proton-coupled electron transfer suppression. Because we will now use an MTE approach for photons, we will be able to go beyond the single photon mode picture to multiple photon modes. So let's start with the first one, with the electron-photon correlated system. So in this case, as I said, it's going to be a super simple setup. We just have a two-level system in a cavity, and we have an excited electron that drops into the ground and emits a photon. And what you see here, the red curve is the exact solution, and the blue curve is the MTE approach, so the classical trajectories for the photons. And as you see, our approach is capable of describing the spontaneous emission. You see the wave packet moving through the cavity, getting reflected, and coming back to the atom. Even more so, if you zoom in on this middle peak at the atomic position, we find that our approach can even capture polar-retardant peaks, which are at the atomic position. The only thing we can't capture right now is the last panel down here, where we find reabsorption and re-emission process. When the wave packet comes back to the atom, re-excites the atom drops again in the ground side and re-emits a photon, which can kind of be related to a branching process in the electron-nuclei interaction, and which is kind of obvious that an Ehrenfest approach can capture this part of a reabsorption. But the good thing here is that there is a whole toolbox of mixed quantum classical methods out there, which we can simply use and to see if we can get more accurate and also better results for this setup, especially because the MTE approach is kind of the lowest version of propagating your system. And that's exactly what we did. So we took different methods and benchmarked them for the exact same setup, and I won't go into detail. I just refer to our publication down here in case you want to know more. I just want to point out two curves. The first one is the orange one down here and the blue one down there. Those are now path integral methods. Those are semi-classical propagation schemes, and in those cases we can even capture to some extent now also some sort of reabsorption re-emission process. And even more so if we go to more complex systems, and again I won't go into great detail, I just want to let you know, even in an MTE approach we are able to capture spatial correlation functions, where now the black colors here now show coherent light, so classical light, and everything which is kind of yellowish shows anti-bunch light, so non-classical light. And already for the lowest version of propagation scheme, the MTE, we are able to capture those non-classical light effects. So in general, I just quickly want to sum up our electron photon benchmarking. So we can include quantized light fields by just simply adding a sampling scheme for the photonic degrees of freedom and then propagating them with classical optical trajectories, we find spontaneous emission, or we can describe spontaneous emission, polariton peaks, and even correlation functions with just using MTE. And if you go beyond the simple MTE approach, you will also be able to capture effects like reabsorption and re-emission. But as I said in the beginning, our main idea of starting to develop this method is to be able to go to realistic systems. So for sure, we also need to include the nuclear degrees of freedom, and we benchmark this whole thing on a Shin-Matthew model in a cavity. So what we're having here now is two fixed ions, the black ones. One ion can move in 1D and one electron can move in 1D. And our idea is to describe the suppression of proton-coupled electron transfer. More precisely, we wanted to check, because we now use MTE for photons, we can go to a multimode setup. How does the suppression of the proton-coupled electron transfer change if we include, besides one resonant photon mode, a lot of off-resonant photon modes? And just to give you a quick overview what the setup is, so this is now the cavity-free setup. So we start with a nuclear wave packet on the left side. It slides down, it splits on the avoided crossing, and if it moves from the left to the right, we talk about a proton transfer, and if it moves from the upper left to the lower right, we talk about a electron transfer, so moving from here to there. Means we talk about a proton-coupled electron transfer. And if you now put this whole thing in a cavity, what happens is part of the nuclear wave packet will drop to the lower surface by emitting a photon, and only the upper part of the nuclear wave packet will move from the left to the right, and part of the wave packet gets trapped on the left side. And with this, we talk about a suppression of the proton-coupled electron transfer, and I will show you how many off-resonant photon modes will change this whole suppression or the whole dynamics of the nuclear wave packet. And if we want to go in a multimode setup, we have to think about two things. First of all, you can think of, in our case, we have two Born-Oppenheimer surfaces. If you include many modes, you can think of shifting your surfaces by the energy of your photon. And in this case here now you see a shift of just including two photons. So already from just having two surfaces, now shifting by the energy of two photons will lead to in total 6 surfaces. And if you start with your surface with your nuclear wave packet here, this will now encounter for a lot of more avoided crossings, and even more so because in our case we will go up to 440 photon modes. You will see that this kind of starts to develop, this whole shifting of your surfaces starts to develop band-like structures, and the overlap of those bands kind of shown here are now all avoided crossings. And with knowing that, we decided to still treat the nuclear degrees of freedom quantum, also the electronic ones, and will only use an FTE approach for photons in this multimode setup, because we really wanted to check what is the effect of many photon modes and not what is the effect of having so many avoided crossing, which is kind of a mess in a mixed quantum classical setups for nuclei. So quantum nuclei, quantum electrons, and MTE for photons. And what you also have to think of if you include many photon modes is the so-called self-polarization term. This term, for a very good reason, is most of the time neglected because it goes in with a lambda squared, so a coupling squared and a dipole squared. And if you don't have crazy dipoles or crazy strong coupling, ultra strong coupling, this term is negligible. Also, in most cases, people only couple to one resonant photon mode, then the sum is also negligible. So in general, this term most of the time doesn't do anything. But in our case, we go up to 440 photon modes, and we first for sure didn't include this term because we didn't think about it, and we found that including or not including this term in a multimode setup completely changes your physics. Here now is the dynamics of your wave packet without self-polarization, and those are the dynamics with self-polarization. If you quickly focus on the black line here, this is now the dynamics of just having one resonant photon mode. With resonant, I mean resonant to the initial state of your nuclear wave packet. So the nuclear wave packet starts on the left side, moves to the right side, part of the nuclear wave packet gets trapped as here in the cartoon, and the other part moves to the right side up here. And if you, and all the colored lines now show the different dynamics of including different photon modes. And as you see here, if you don't include the self-polarization, you see no structure at all. We didn't find any correlation between including more photon modes and seeing what happens in the dynamics. Even more so if you look especially at this time snapshot here, the blue one is 440 photon modes and the black one just one resonant photon mode. And we see even less suppression, and at the end it spreads all over the place, which we started to explain because we have so many avoided crossings here when nuclear wave packages spreads everywhere. But then we started to include the self-polarization term, and all of a sudden physics started to make sense, because now we see a strong correlation between having a suppression and including more photon modes, because what we see now is the more photon modes we include, the more we suppress our proton-coupled electron transfer, up to the fact for the 440 photon modes where we completely suppress or keep the nuclear wave packet on the left, so completely suppress the proton-coupled electron transfer. And to make it a little bit more dramatic, this is now the nuclei dipole, and the dashed lines are the lines without self-polarization, and the solids one are with self-polarization. And here you see that not only quantitatively there's a giant difference between including and not including the self-polarization, but also qualitatively. If you go from dashed to dashed here, we will find an increase of the proton-coupled electron transfer. If you go from solid to solid here, we will talk about a decrease of the proton-coupled electron transfer. So including or not including self-polarization not only quantitatively but also qualitatively completely changes your physics. And to kind of show the impact of the self-polarization, we now introduce the so-called self-polarization modified Born-Oppenheimer surfaces, which is a very simple setup where you just simply take your Born-Oppenheimer Hamiltonian and add the self-polarization and solve your eigenvalue problem, or calculate your surfaces, and what you get is the following here. And here you really see why the self-polarization is that important, because in the 10-mode case, the Born-Oppenheimer surfaces and the self-polarization modified Born-Oppenheimer surfaces are kind of on top of each other and the dynamics are the same. But the more photon modes we include, the more different those surfaces get. Not only changes the position of the avoided crossing from around 2 to around 0, it also opens up dramatically, and most importantly, the slope changes from going downwards to going upwards and kind of trapping your whole wave packet to the left side. And those are now the main points I want to make with this. Is now, first of all, including many modes, even if they are mainly off-resonant, changes your physics. And if you do so, you have to be very much aware of the self-polarization, because it not only quantitatively but also qualitatively completely changes your result. And with realizing this, we also realized, okay, perhaps the self-polarization, or the number of photon modes, is an interesting tool to control and change your chemical reactions, because we see a full suppression of the proton-coupled electron transfer without even touching the coupling strength. We only included more photon modes. With this, I hopefully was able to kind of advertise our new method, the MTA approach for photons, which is based on the idea which is already done in great detail already for the electron-nuclear interaction. So it's a mixed quantum classical approach for photons, where you just simply sample your photons, and if you do so, you will be able to capture spontaneous emission correlation functions. And if you go beyond a simple Ehrenfest approach, you can even capture to some extent re-emission, reabsorption processes. And I unfortunately wasn't able to talk about this, just for in case someone is interested. We also looked at this whole thing in the framework of exact factorization, where we looked at time-dependent potential energy surfaces, where we found that photonic potential energy surfaces, even if you think they are harmonic, they are not that harmonic. And then I also explained, or we also started to extend the whole thing to the nuclear degrees of freedom again. We also investigated this whole thing in the exact factorization framework. Again, didn't have time to talk about it, but just in case someone is interested. And the main point I wanted to make today is the effect of many modes, even if they are not resonant to your system. In our case, we found that there is a giant effect of the off-resonant modes, and especially if you go in a many-mode setup, the self self-polarization becomes extremely important, and perhaps also gives us a new tool to control and change chemical reaction, because we see a full suppression of the proton-coupled electron transfer by simply including more photon modes instead of changing the coupling strength. And as I kind of in the beginning gave a short motivation of saying, oh yeah, we want to develop ab initio methods, and I wasn't ab initio at all, it was just like benchmarking of model systems. For sure, this is now our next step. We want to couple this whole thing to an ab initio calculation for the electronic structure. Also in the many mode case, we also treated the nuclei for a good reason quantum mechanically. We for sure also want to go to a sampling method there for the nuclei degrees of freedom, but here we have to be really careful because as I said in the beginning, our nuclear wave packet will encounter a lot of avoided crossings if you have many photon modes, and we will need a method which can deal with a lot of avoided crossings. And with this, I want to thank my collaborators from Max Planck and from Rutgers University Newark and my funding. And in case you have any questions, concerns, or just want to know more about it, feel free to write me here to this email. And thank you very much again for your attention.